Okay, so if there are no questions, we'll jump into our discussion that we kind of started last class. And so in the slides, what you will see is I'm going to do things a little different. So what we have done so far, at least in this topic, is that we have seen how to estimate parameters for a Bernoulli distribution given some data, right? And then we also looked at the notion of posterior and prior. Typically, after that, what I do is I discuss how to do the same kind of process. So, estimating parameters for a different distribution. In this case, it's more of a Gaussian distribution, right? However, so, and the approach is similar, right? Because even for a Gaussian distribution, you have some equation for a likelihood, right? So you have this is your random variable, which is x, and then it has two parameters, mu and sigma. And then you can do MLE on this. So we will look at it maybe next Wednesday. It's a similar procedure, except that the math is a little different. So I just want to do it still because but I will do it then, because after that we will talk about Gaussian discriminant classifiers. So those are related. So that's why I think that would be better. Today what I'm going to do is I'm going to jump into part 3, which is about Bayesian classification, because that kind of flows with what we've done in the last class. All right. So that's just a minor change. All right, so this is sort of the whole overview. And essentially what we are going to do is we are going to look at one of the classification algorithms in this category. It's called naive Bayes classification, all right, or classifiers. Okay, so let's go here. All right. Any questions so far? All right. So we have last time what we've done is we have done something where I said that if I give you our job was to estimate what is the probability of heads, the theta, right? So every coin, the output of a coin, you can think of it as a random variable, which is it takes two values, head or tails, and then there is and we say that we model those heads and tails using a Bernoulli distribution. Each Bernoulli distribution has a parameter called theta, and that theta tells you what is the probability of heads, right? And then we saw how to estimate that theta given some training data, right? So today we are going to make it a little more interesting. We are going to say, let's say you have two coins, okay, coin 1 and coin 2, all right? And what we want to do is, given some training data, we want to learn the parameters, but the question we want to answer is that when I give you a new toss, okay, so let's say I give you a training data set in which your x, your observation is it a heads or a tails, right? So let's say it is heads, 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 tail, tail, heads, heads, tail, heads, right? This is your observations. But for training data, we also have the true label. In this case, our label is, was it coin 1 or coin 2? So here there are two coins, okay? One is a quarter and one is what is this? Some 2 euros, okay? So there are two coins here, and we are assuming that they are not fair. That means it's not like both of them have theta equal to half. They both have some theta, okay? Theta 1, we don't know what it is, and theta 2, we don't know what it is, right? What we have is some training data in which we have these observations, and we also have the class. And the class is which coin it came from, okay? So we'll say for this one, it came from coin 1, and for this one, and this one came from coin 2, coin 1, 1, 1, 2, 1, 2, 1, all right? So let's say we have some data like this, all right? And what we want to do is that next time I see a new toss, it's a heads, and you have to tell me what is y, which coin did it come from, right? So that's a classic classification problem, right? So if I replace these x's with the features that we have seen so far, like if we go back to our tumor example, these x's could be the observations, right? This is what was it? Dark red and irregular. This could be something, 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 and this y could be malignant or benign, right? So it's the same setting, and then I give you a new observation, and you have to tell me if it's malignant or benign, right? So it's the same setting, but here we are trying to make it a little simple. We are saying, okay, we have only one of, I have only one attribute, which is it a heads or a tails? And the class label is it coming from coin 1 or coin 2? And so we have to learn these thetas so that then we can predict what y is, right? So what we want to find out is what is the probability of y to be coin 1, right? Given x star is equal to h, right? And then we also want to compute what is the probability of y equal to 0 given x star equal to h, right? And whichever is higher, of course, these both will sum to 1. So estimating only one of them is enough. But whichever is higher, we'll say it has come from that coin. So this answering this question will tell us which coin it came from, right? Sorry, 2. Right. Equal to 1. Yeah. So now, how do we compute this value, right? And we have seen that. We can apply Bayes' rule. We can say that the probability of y equal to 1 given x star is equal to h is equal to probability of x star equal to h heads given the coin was the first one times prior probability of y to be 1 divided by x star equal to h given y was coin 1 times probability y equal to 1 plus x star equal to h given y equal to 2 y equal to 2, right? So you all should be familiar with this expression. There's nothing much to it here. It's just application of Bayes' rule, right? Conditional probabilities and Bayes' rule, right? Of course, what you can see is that, as I said, right, and then you can compute y equal to 2 also in the similar way. It will just be different. Let's write it anyway. Heads given y equal to 2, py equal to 2, and then this denominator would essentially be the same thing over here, right? Same thing repeated, which means that if you want to just find which one is higher, you can just compute a numerator, right? And that would be it. But if you really want the probabilities, then you want to divide it by this so that these sum up to 1, right? Okay, so now comes the question, how do we compute these things, right? So first we want to find, okay, what is the probability of x star to be heads given y is 1, right? Which is, what is the probability of observing a heads given that the coin is the first coin, given the coin is the quarter, not the euro, right? This we have done. In the last class, this is exactly what we tried to estimate, right? For first coin, what is the probability of observing this? So this can be written as, so now what we typically do is, we look at this training data, and we only take those rows in which the coin was 1, right? So this one, this one, this one, this one, this one, this one, right? So that one, so the data for the class 1 is heads, heads, tails, tails, heads and tails, right? Oh, sorry. So this is my class. So in last class, this is essentially what we did, right? Given some training data, estimate the parameter. Because what is this? This is essentially the theta for class 1, right? So, sorry, here, so heads, heads, tails, tails, heads, heads, right? Sorry, thank you. Yeah. So this is my training data. Now we know many ways to do this, right? Because in last class we said, you can either do this as a map estimate. So you can use theta 1 as the map estimate or the maximum prior estimate or MLE, right? Or you can do Bayesian averaging to get this value directly, right? So each one of them had certain value, right? So if you remember, if you just, so let's say we assume a prior on this, on the tosses. So let's say it is a beta with some A1, B1. Right. So now this value can either be a1 over a minus 1, a1 plus b1 minus 2. If you using the max prior, it could be just the number of heads, so which will be 4 times 4 by 6. If you are using MLE, it will be 4 plus a1 minus 1 over 6 plus a1 plus b1 minus 2 if you are doing map, and I think it was 4 plus a1 over 6 plus a1 if you are doing Bayesian averages, right? So this is, don't get overwhelmed with this. This is essentially what we computed in last class. So if you refer to your notes from last class, you will see that. But the main point that I'm trying to make is that you are trying to estimate which coin was it given the observation, and that can be computed like this. And this part of that is essentially theta 1, which can be computed by just looking at the data for this. And then the same thing you can do for the coin 2, right? So you just take the second coin, and then you repeat the same process. Yeah. So what I want you to think is that this is exactly how you would, as humans, do the same thing, right? So the question I'm asking you is that I have tossed the coin many times, both of the coins, and this is what I have observed. And now I say that without showing you, I toss one of the coins. I don't tell you which coin, right? And I got a heads. So now you have to tell me which coin did I toss. So what would you do? You would look at the first coin and you'll say that the first coin typically gives more heads than tails. It gives 4 out of the 6 times you toss the first coin, you saw 4 heads, right? So maybe the maximum likelihood estimate for that is 4 by 6 or 2 by 3. Whereas if you toss the second coin, you saw 2 heads out of 3. So it is 2 by 3 again. Sorry, it's a bad example. Let's call this heads as well. Okay, so then what you see is that you see a heads every time, right? So 3 out of 3 times for the second coin you saw a head. So then you make up in your mind that the second coin gives more heads, or the likelihood of getting a heads from the second coin is higher. So then what you do is, if you observe a head, you will say, okay, the probability that it came from the second coin is higher, right? So that is how Bayesian classification works, right? Any questions so far? All right. So, and then what we will do today is we are going to expand this to a more complex problem. But before that, I also wanted to make another point, is that, of course, we have already seen how to compute this value. This is the class conditional probability. But what is this value, right? So this is, what does this say? What is the probability of the coin to be the first one? Yeah, which means it's basically, you're saying, I'm not going to give you any training data. Well, I'm not going to tell you what you observe. So which coin would I have more likelihood of observing? So that essentially means you basically count how many times you saw coin 1 and how many times coin 2. So for example, here, the total number of examples we had was 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of 9, you saw the coin number 1 being tossed 6 times, and the coin number 2 was tossed 9 times. Right? So this was coin 1, coin 2. Sorry, 3 times. So there's a higher probability, even if you don't see what the coin was, right? So let's say I give you a slightly simple. Let's say in your training data, let's say your training data was like this: heads, 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 tails, tails, heads, heads, heads. And so this was X, and Y was coin 1, coin 1, coin 1, coin 2, 1, 1, 1, 1. Yeah? So what this tells you, this training data tells you, is that coin 1 tends to be tossed more, right? Which means that if I ask you what is the probability that a new example would come from coin 1, just by looking at this itself, you can say, you know, there is a greater chance that it is coming from coin number 1. Why? Because in your training data, you see more labels with that, right? So that essentially is what this probability is. This is essentially how many times in the training data you saw number of examples with coin 1 divided by total number of examples, right? So now what you can easily do is that with this training data, you can compute these probabilities because you know what this is, you know what this is, and these are essentially the same thing. Yeah? Any questions so far? All right, thank you. Good. So let's move on. Where am I? So today what we are going to do is we are going to make it a little more interesting, okay? So I gave you the coin example, but that doesn't look very interesting, right? That doesn't look very useful. Why do you want to predict which coin it is? But let's look at this one. We have seen this before, right? This is the data that we looked in the first 2 weeks, right? So here are your observations. So you're trying to predict if a tumor is benign or malignant, yeah, by looking at some properties that it has. So in this example, we say that a tumor is defined using or described using 5 attributes. Each attribute is binary for us right now. So it could be either circular or oval, large or small, light or dark, smooth or irregular, thick or thin, right? And this is your class label. Yeah. So this translates. This aligns very well with the coin example, right? In the coin example, all you were looking at was it a heads or not? But here we are looking at multiple features, and then these are the labels. So this is again coin 1 or coin 2. And what you want to predict is that given a new X star, you want to predict if it's a benign tumor or a malignant tumor. So if you were doing something like a neural network or a perceptron, you would be doing some kind of a functional approximation, right? You would say, okay, Y star is W transpose X or sigmoid of W transpose X and so on. But here, in Bayesian classifiers or a probabilistic classifier, which we are looking at today, we are going to say what is the probability of the class to be benign given this is your observation, and class to be malignant given this is your observation, right? So the expressions are exactly what I showed you earlier for the coin example, right? So the first thing is, so here's another example. So let's say, I don't know why I hit those. All right. Oh, okay. Yeah. So let's say in your training data, you have 3, what are these, malignant tumors and 2 benign tumors. And here comes a new tumor, and you have to find these probabilities, right? Now, what we do in Bayesian classification is that we assume that this Y, right, the prediction also is a random variable because it can take 2 values, benign or malignant. So we say that that also is a random variable, and we assume since it's a binary random variable, we assume that it is being generated by a Bernoulli distribution with a parameter theta. Okay, so the question becomes, how do you estimate theta? So one thing you can see is that you can easily, without even looking at what the values of these examples were, you can compute the probability of Y to be 1, which is that basically you count, okay, out of 5 times you saw 3 heads or 3 malignant tumors. So the probability of Y to be malignant is 3 by 5. Yeah. However, and then you can also add some prior if you want to, right? Let's say somebody tells you that there is a prior information about malignant and benign tumors that people know of as a domain in expertise. So then you can combine them using this expression. So remember, this is an expression that comes by doing the Bayesian averaging, right? So you can come up with what is the probability of Y to be malignant, which will be theta, and Y to be benign, which will be 1 minus theta. And you can use that to make your predictions. But those predictions are not really using the values of X, right? All they are using are how many blues you take and how many in the training data, how many malignant tumors you saw and how many benign tumors. So that is what I showed you earlier, which is probability of Y equal to 1 and probability of Y equal to 2, right? That's the prior probability for these things. But now we want to also compute the other values. So we call that the posterior for Y. So remember that without looking at the values in the training data set, you can get a probability for Y equal to 1 and Y equal to 2, right? Which is this. But this is what we call the prior estimate because we have not really looked at the training data yet. Now we are going to compute the posterior. So we are going to say, okay, now if we also look at the values that the x's took, can you recompute these values, right? So that would be, not this, not this, that would be this, right? What is the probability of y to be malignant given x equal to x star? Remember, because x star in this example is this, right? So what is the probability of y to be malignant given x star? And that in a Bayesian setting can be written as this. So this is exactly what I wrote earlier for the coin example, which is probability of x to be x star given that we know the class is malignant times probability of y to be malignant divided by this and this and this, right? So we have already seen how to compute this in the previous slide, right? Which is you basically count the number of malignant examples here. So P of y equal to malignant in this example would be 3 by 5. But now comes the question, how do you compute this? Probability of x equal to x star, y equal to malignant. Yeah? All right. Okay. So, we want to compute what is probability of x equal to x star given y is malignant, right? Where x star, where each x, right, is a sort of a vector, right? It could be small, comma, whatever, dark, comma, irregular, thin, and so on. So now this becomes a little different than the coin example, because in the coin example, your x's were just heads or tails. So you could easily compute those probabilities as a Bernoulli random variable, right? But now your x's are no longer a single binary observation. It is a vector of binary observation, right? And Bernoulli distribution is not defined for a vector of binary observation, right? So what do we do in this case? And that is where everything becomes more interesting. Any questions so far? Yeah. This one? Oh, I see. Yeah. Any other questions? So the thing that you want to appreciate here is that we have seen how to compute. We have the expression to get these posterior probabilities because these are the ones that you will use to make your prediction. So we have the expressions here. This part is easy to compute. This is the prior probability on the class, right? Knowing any training values of the training data, you can still compute this. But how do you compute this, right? Because this depends on what type of random variable this is. In this case, in this example, this random variable was a binary random variable, which meant that you can model it as a Bernoulli distribution, right? But now in our tumor example, it is no longer a Bernoulli distribution because your x is actually a vector, right? Each one of these elements in the vector is a binary variable, but they're all together, right? So what you want to compute is this joint. So essentially what you want to compute now is probability, a joint probability. What is the probability? Let's call each one of these elements as circular large. Okay, there's a circular here. So there are 5, right? So let's call each one of them as 5 random variables, x5, right? So this probability is essentially a split. It's a probability of x1 to be circular, x2 to be small, x3 to be dark, x4 to be irregular, and x5 to be thin. Or given that your class is malignant. So you have to compute this joint probability distribution, right? Because your random variable is actually composed of these 5 random variables inside. So you need to compute this joint probability distribution. Okay? Now how do you compute that, right? So that's the interesting part. All right. So if you think of a probability distribution for these kind of random variables, those are essentially, you can create a table, right? For example, what you can do is, let's say, let us assume that x was just a single variable, which was x equal to, it could either be small or large. That's all, right? So you can compute the probability of x. So x was just x1 or x2. So you can compute, you can represent this probability using two numbers. One is, what is the probability of x2 to be small and x2 to be large. So let's say this was 0.7, 0.3. So this is the probability distribution for x given y equal to malignant. You need two now. Actually, you just need one number. The other one is 1 minus of that, right? But if x is just x1, but if x is actually a vector of two random variables, x1 and x2, then what do you need? Then you need a matrix. Then you need, this one will be x1, and this will take two values, let's say circular and oval, and this one will be small and large. And then you need four values here, right? So you will need 0.7, 0.3, 0.2, 0.8, something like that. Yeah. Well, I don't know. They have to sum to 1. So 0.4, 0.3, 0.2, so now you need 4 minus 1 values. Oh, sorry. Right? Okay. Now let's expand it. What if we have 3 random variables inside? So the joint probability distribution now will have, it will be a cube, because you have to, you need to encode all possibilities, right? So instead of drawing it as a cube, I will say we need to compute what is the probability of small, comma, circular, comma, dark. You need to compute probability of small, comma, circular, comma, light, and so on, all combinations, right? So now you will need 8 minus 1 probabilities to store it, right? So this can go on. So if you have d attributes, right? So to compute this joint probability distribution, you will need 2 to the power d minus 1. So sorry, go here. So in general, if x is composed of d binary variables, we need 2 power d minus 1 probabilities for the joint probability distribution. Right? Is that clear? Because a joint distribution is nothing but probabilities for all possibilities, right? So if you have a joint, if your variable takes multiple attributes, then you basically have to encode the probability for all possibilities. So if you have d random variables inside this one big random variable, each one of them is binary, then you can have 2 power d possibilities, right? Because you can have, that's simple combinatorics. But since these are probabilities, they have to sum up to 1. So the last value you will know if you know the first 2 d minus 1 values. So which means that you need 2 power d minus 1 probabilities to describe your joint distribution, or this full joint distribution. Any questions so far? The point I'm trying to make is that this is too complex. You cannot maintain so many values, right? Because d, if d is very large, right? So for in the tumor example, d is 5, so it's just 2 power 5, right? Which is easy, okay? 32 minus 1, 31 values. But what if d is 100? Now suddenly you have to maintain this huge, distribution, which is not efficient, all right? The second thing is that we have is that you also need a lot of data to estimate this. So that goes back to that black swan paradox, is that now if you want to estimate all of these values, right? If you want to say what is the probability of small circular dark, small circular light, which means that in your training data, you should have seen enough examples of each possibility to compute those probabilities, right? So if your D is very large, that means you need a lot of data to estimate this as well, okay? So that is the main point, right? And now this becomes even more severe if we are trying to estimate these probability distributions for each class, right? So you want to compute this value for y equal to malignant, and you also want to compute this value for y equal to benign, right? So which means that for a binary classifier, we need 2 times, because for each class you will have a distribution 2d minus 1 probability. All right, so this is too complex. Any questions about this? So this is an important point, which maybe in this course we might not see it over and over again, but in general machine learning, that becomes a big problem, is that even though these probabilistic classifiers look very attractive, the problem is that when you have to model these joint probabilities, sometimes they become too complex. For example, here, yeah? So that is, so this, that motivates our next thing. Right, so this is pretty much what I said today. So now we will look at a classifier called naive-Bayes classifier, which tries to alleviate that problem. So what was the problem? The problem was that if you are trying to model this joint distribution for an x, which is actually composed of many random variables, then the joint distribution needs too many parameters, which is exponential in D. In computer science, if there is anything which is exponential in something, you run away from it, right? So even here, it's 2 power d minus 1 times 2, which means 2 issues. One issue is that you have to store it. That itself becomes a challenge. And the second issue is that to reliably estimate those probabilities, you need a lot of training data, because you need at least a few samples for each possibility to say, okay, this is the probability, right? So you need a lot of training data. So those two are why we look for simpler solutions. Another thing is that this is also too complex. All right. So now we are looking at naive-Bayes classifier, which tries to solve that problem by making an assumption. The assumption that it makes is that all features are independent. Okay, all attributes are independent. What does that mean? It means that you can write this probability. So naive-Bayes assumption, or naive Bayesian assumption, I forget. What it says is that the joint probability of x1 to be circular, x2 to be small, x3 to be dark, x4 to be irregular, and x5 to be thin, given y is malignant, can be broken down as given y equal to malignant times probability of x2 equal to small given y equal to malignant, and so on, right? So remember the independence assumption. What does independence mean? Independence means that if you have two random variables and they are independent, then p of a comma b is p of a times p of b, right? So, and if you have multiple, then it's just a product. So that's what we are saying. What we are saying is that each attribute is independent of others given the class, right? Because here is a conditional thing here too. So these naive-Bayes assumption is not saying that they are all independent. They are all independent given you know the class. So remember our discussion on conditional independence 3 classes back. So that's what comes here. So what that lets us do is that now suddenly you can model each one of these random variables as a Bernoulli distribution, right? So which means, so each Bernoulli distribution here will need one parameter, right? Each Bernoulli distribution has one parameter, which is theta, which means now suddenly you just need, now we need only d parameters, 2 times d, because you have 2 classes, 2d parameters. So by making that assumption that all your attributes are independent of each other given the class, you suddenly go from these many parameters to only these parameters, right? So your job becomes really easy. So that's the naive-Bayes assumption. All right. Any questions so far? All right. So mathematically, this is how we write it. We say that the joint distribution of this random variable given the class is just a product of each individual attribute given that class, and you just multiply them up. So now we will see how to train naive-Bayes classifier. Okay. So essentially what we want to do is to train a naive-Bayes classifier, we want to find the parameters, right? Now what are the parameters now? The parameters are essentially, because each one of these random variables is being modeled as a Bernoulli random variable separately, which means that you have one parameter per class for each one of them. So you have 2D parameters. So we have to train them. We have to find those given your training data, okay? And it's pretty easy. So the parameters that we need are, let's say in our tumor classification problem, you have two classes. So you need the theta benign and theta malignant, which are basically the individual probabilities, and you need the class prior probability. And after that, you can simply apply this and you can get the value. Right? And this is done, I'm not going to go in this math too much because it's fairly easy to do. So the training algorithm is very easy. Okay, so we'll go into that directly. But I just want to show you how we come to that. So essentially, what you do is you say, let's try to compute the likelihood of your training data given all your parameters. So what will be your likelihood of your training data? The likelihood is nothing but the product of probability of each example, right? Okay. Okay. So what is likelihood of a training data set of some D? This is our training data in a naive-Bayes classifier, right? BC. Oh, sorry. All right. So remember, the likelihood of a data set, usually we denote it with L, given some parameter. So right now I'm using this big uppercase theta to express, to contain all the parameters that are associated with this model, okay? So don't worry about what it actually is. It's basically is everything. Is usually written as the product to n probability of each data point given this theta, right? That's simple. Now, what is this probability? Now, this I should put it here. So this is the ith training example. So this is a vector, right? Now, under naive-Bayes assumption, what we have said sorry, if I just had that thing that those people in Men in Black have that erases memory for a bit. So just forget about what I said for last 1 minute. All right, so let's cancel that. All right. So before that, we say what is D, right? What is our training data? Our training data is a set of tuples, right? You have x's, which are your attributes, and the class label. Then you have second one, and so on till x of n, y of n. Each one of them is a vector of observation, right? So we need to compute the likelihood of this d comma theta, which will be product of probability, joint probability of these both, right? So x of I, comma, to x equal to x of I, and y to be y of I, given this theta. So we want to compute the joint probability because we are computing the likelihood of the data set, not just this part, the entire data, right? And of course, we assume that the class and these labels are independent of each other. So we can break it as P of x equal to x of I given theta times P of y equal to y of I given theta, right? Then what we do is, remember now, by the naive Bayes assumption, this can be broken up. So let's say we use the J index to denote the attribute. So probability of xj to be jth value of this ith example times, so this goes here, times y equal to y of I given theta. All right. Now what you see in this expression is that you know each one of these values. So this one, we are modeling our output variable as a Bernoulli distribution, right? So that will be the py equal to 1 given the class. And each one of these are also Bernoulli distributions, right? So now, essentially what you do is to compute all of the parameters, right? So what are the parameters? You have a parameter associated with this y, and you have one parameter for each class for each one of these attributes, each of the d attributes. So you have 2d plus 1 parameters total. Now to compute that, what you can do is you can maximize this likelihood, right? So that's the MLE approach is maximize LD given theta and find the theta that maximizes that value. So it's inverse of what you're doing today in your assignment where you're minimizing the error. Here you're maximizing the likelihood, right? So I'm going to skip the derivation because the derivation is too involved and anyway it really helps our discussion that much. But I want to leave it at the point where I say that, you know, we know all the expressions and now we can maximize it. We know how to maximize things. We set it to the derivative to 0 and you can get the exact expression, right? But the exact expressions you can, as you know, using common sense also you can get those things, right? So there's a whole example here. Yeah, so let's look at the example, right? So let's say this is your training data, right? And this is your test example, okay? So there are two labels, malignant or benign, and you're trying to predict what will be the label given this is my training data. So in this example, I have only 3 attributes, and each one of them is binary, all right? So let's try to work through that, and that will sort of be a little more intuitive to understand. I don't have much time. Because I want to show you this data as well as work it out here, so you can get the printout. Okay, maybe we can we will do it in the next class. But today, the point I want to stop at is maybe just go through it in the general terms, right? So what you want, the things that you want is, number one, what is the probability of y to be malignant and y to be benign? That's the prior probability, right? That you can get by just counting how many malignant are here on the right hand side. So for example, in this example, you have 1, 2, 3, 4, 5 malignant and 5 benign, right? So the probability of y to be malignant is half, probability of y to be benign is half. So you can get that. Right? The second thing you need is, what is the probability of shape to be circular given type is benign, right? So typically what you do in that case is you only look at the rows which has benigns, right? 1, 2, 3, 4, 5. And in that, you see how many times do you see circular. So for example, in this one, you say circular 2 times out of 5, right? So 2 by 5. That's the probability of y to be shape to be circular given benign. And then the same thing you keep doing for the other attributes as well. So that essentially is the naive Bayes algorithm, right? So what you do is, you have the training data, right? From the training data, you first find out what is the probability of Y to be malignant and probability of Y to be benign, which will be just 1 minus that. This can be done by just counting how many malignants you see divided by total. And this will be the other way, right? That is easy. And then you see, then you do it for every, then you say, okay, what is the probability of shape, that's the first attribute, to be circular given Y equal to malignant. So how will you compute that? You will basically look at all the examples which were malignant, and in that you will say how many times did you see circular, and that will be that. So you will say, okay, how many times did you see circular in malignant examples divided by how many times you circular in malignant plus how many times you saw benign oval in malignant. And that gives you that probability, and so on. So you list out all the probabilities, right? You will have to list out 2 power d plus 1, which in this case it will be 7, right? So you'll need 1 here, you need that probability, then you need 2 for each attribute, and that's it, right? After that, now your test example, let's say your test example is circular, small, light. So what you will, and now you want to find what is the probability of Y to be malignant given this X is X star. This can be written as probability of X equal to X star given Y equal to malignant times probability of Y equal to malignant divided by that normalization constant, which is, we'll talk about later. But this you have, this is this, right? And then this can be broken up because this is a naive Bayes assumption. So this will become probability of shape equal to circular given Y equal to malignant times this value times times probability of the second one, whatever, size equal to small given Y equal to malignant times color equal to light Y equal to malignant times this prior probability Y equal to malignant, and so on, right? So it's, now you can get the probability. So that's how the naive Bayes classifier works. All you need to do is count. It's a simple counting procedure, right? In fact, if you look at this algorithm, this is what it's asking you to do, right? So it's written in a mathematical form, but all you're trying to figure out are the different counts. How many times do you see this value? How many times do you see the other value? And at the end, you get all these probabilities, and then you can use them to predict the probability of a class given a new training, given a new test exam. All right. I think it will be a little more clear when we run through this example on Friday. So don't worry about it too much right now. But you do want to understand it well because you will. There is a problem in gradients this time for this kind of problem. Okay. Any questions so far? Okay. A reminder.